If I add a light bulb to this simple circuit and it lights up, does the bulb eat or use up the electricity? Not quite. The current actually flows all the way back to the battery, and this squiggly thing in the light bulb, this is a resistor that simply slows down the current. For a simple light powering circuit, we have the light bulb or the resistor, but we'll also need a wire, a battery, where current comes out the positive in the negative, and a light switch, which is optional, but open it and the circuit stops. Before looking at the equation, imagine the circuit as a downhill obstacle course for kids. The battery is like an elevator whose job is to lift the kids up, up, up to the top of the hill, where higher up means more elevation or more potential energy to run back down. Now, the downhill slope is what drives the race, and so the greater the height, the greater the slope, the greater the potential energy in the battery, the more this circuit will run. If the slope was completely smooth, they would fly down too quickly. Boring. So let's add some obstacles. Mud puddles, trees, a river. Now that's an obstacle course. More fun, but more obstacles to slow them down. These obstacles are the resistors, and to get through them, the kids have to slow down. They have to fight through it. And when they get to the bottom, they're spent. So what do we actually have here? The elevator, our battery, that's our voltage. Measured in volts or joules per coulomb, this gives us the electric potential energy per unit charge. The electric potential energy, or the elevation, is simply the difference in height from the top to the bottom. So if this elevator is a 3-volt battery, a 9-volt battery would take us 3 times higher. The greater the voltage, the greater the potential, the more energy the kids get to run down. But that also means the voltage drop is greater because as the kids run the course, their energy is spent at the bottom. Next is our current, I, which is measured in amperes or amps, which is coulomb per second. Remember the kids running down the course? A coulomb, C, measures a specific unit of charge, Q, which is about 6 times 10 to the 18 electrons. The kids are not the coulombs. Instead, we're looking at how many kids pass the obstacle per unit of time, per second. When I ran the New York City Marathon, the timing mats didn't just count runners. They tracked exactly how many chips crossed the line at any point in time. If the kids are running single file, so their pace is the same, they're all slowed down together, a current of 1 amp is 1 kid passing each obstacle at a moment in time. A current of 5 amps is 5 kids crossing each obstacle at any given time. Which brings us to our obstacles, the resistors. As the name implies, they resist or slow down the flow of charge, and they're measured in ohms, the Greek letter omega. Resistors are typically shown as a zigzag on your circuit, but sometimes they're shown as a lazy box with a resistor inside, or an actual object like a light bulb acting as a resistor. I mean, doesn't that shape look like an obstacle course for the current? This small puddle of mud, 10 ohm resistor. This giant river, 100 ohm resistor. The more obstacles that I add, the more the kids have to slow down, which means fewer and fewer kids cross the finish line every second. Which brings us back to our simple circuit, where we have our battery, our resistor, and the current flowing through. In the real world, everything has some resistance, even a copper wire, but for the MCAT, we're going to assume that wires have no resistance and therefore doesn't slow down the current. So we have voltage, current, and resistance. How do they actually connect? Looking back at the obstacle course, the speed of the kids on the course, the current, depends on the balance between the two forces. The voltage, how much potential we gave them at the top, meaning how high did they go, and the obstacles or the resistance holding them back. Now the MCAT loves relationship questions, so let's predict the outcome before we look at the math. If I hold everything steady, but increase the height of the hill, I increase my voltage. The kids have more energy, they have more push, they run down faster. That means the current goes up. If I lower the hill, I decrease voltage, they can't slide down as easily. The current goes down. If I keep the height the same, but I add more trees, rocks, and mud puddles, it gets harder to navigate and the current goes down. If I remove all the obstacles to decrease resistance, the kids fly down the hill, current increases, and then they get bored and kind of just quit. This is the logic behind Ohm's Law, V equals IR, where V is measured in volts, I is current and R is resistance. Now practice is what makes it stick. So comment worksheet below and I'll send you my resistors and capacitors worksheet. One trick to remember this is the V equals IR triangle, where you pick any one unit and the equation is right there. The initial equation, V, is equal to IR. If I want to solve for I move R to the other side to give me I is equal to V over R. And if I want to solve for R, I move I to the other side to give me V over I. Say you're given a circuit with a 10 ohm resistor and a current of 2 amps. What's the voltage? Meaning, what's the force needed so that the current can get through the resistor? We need V, so we plug in IR. That's 2 times 10, 20 volts. This tells us that for kids to go down this obstacle course with a 2 amp speed passing through a 10 ohm resistor, they need an elevator that is strong enough to give them 20 volts to the top. But the MCAT won't be so nice with their numbers. What if you have a 12 volt battery, a 12 meter hill, and a 5 ohm resistor? How much current is flowing? Using V equals IR, we isolate I, giving me I equals V over R. 12 over 5 on the MCAT, ouch. But we have a few options to solve this without a calculator, which I teach in my math videos linked below. I can estimate that 12 over 5 is between 10 over 5 and 15 over 5. Somewhere between 2 and 3, so we'll guess 2.5. Or, because we're dividing by 5, I can use the trick of putting it out of 10, multiplying by 2 over 2, which doesn't change the identity, but gives me 24 over 10. Then I use the decimal trick to move the decimal back 1 space, top and bottom, giving me an exact answer of 2.4, which is pretty close to 2.5. And on the MCAT, close enough is good enough. Now what happens if I add a second resistor to the circuit? Or worse, I branch the circuit and add the resistor here. That's exactly what we'll cover in the next video.